Morning, everyone, and thank you for inviting me to talk. Very interesting meeting here. So I'm going to talk about properties. Is it enough? Some?
You have to speak up.
Yeah. Is it on?
Yeah, it's on.
Yeah, it's on.
Better? No? Maybe I should keep my... Maybe it's not convenient for my neck. So I'm going to talk about properties of ultra-cold polar molecules and highly magnetic atoms that are relevant for many-body physics. I would like to acknowledge the contribution from members of my group at Temple University, Kostas Makridis and Alexander Petrov. So, quantum gases of ultra-cold polar molecules and magnetic atoms are proposed to be good candidates for simulating many-body states. And recent years, these systems are confined in optical potentials created situation when exotic phases of solid states could be observed. They became powerful tool for simulation many-body physics. In my talk, I'm going to address several outstanding issues related to collisional interactions and optical control of these species. And I will talk about highly magnetic atoms, metastable atoms, metastable alkali earth atoms, and polar molecules. For all these three cases, I will talk or discuss the role of anisotropy in polarizability and interactions. And these properties are important, essential for simulation exotic phases such as spin lattices, liquid crystal phases, and others. So in optical lattice is created by counter-propagating laser fields where atoms and molecules confined in periodic potentials, and the strength of this potential is proportional to the laser intensity and polarizability. For atoms, for example, if orbital angular momentum is non-zero, then entropic potentials become dependent on internal states. A good example of such atoms are submerged shell atoms, rare earth atoms actually, and as well as alkali earth metastable atoms. The same is true for rotating actually states of the molecule where polarizability are different for different magnetic sublevels, and it could lead to different real space potentials. It became possible to use Raman transition to couple different spin states in order to initiate state-dependent lattice manipulation. I will talk about a little bit about dynamic polarizability. Dynamic polarizability of atomic or molecular level is due to dipolar coupling to all other levels or continuum states. So we calculate dynamic polarizability different ways. For atoms, for example, the most convenient is to use a well-known, accurate experimental information about transition frequencies or oscillator strengths. The same time for molecules, you may not find enough information from experiment. Therefore, theoretical ab initio calculation is very important here. So we can calculate potential energy surfaces, permanent transitional dipole moment, then we calculate raw vibrational spectra and all these transitions and transition dipole moments vibrationally averaged. So we use this method as well. And then we used also just a couple cluster method, which also calculate dynamic polarizability ab initio, but having this method results, we don't really distinguish contributions from different potentials, but it's very convenient to use this method. So I start to discuss role of anisotropy in polarizability from most magnetic and most anisotropic dysprosium atom. So dysprosium atom has unfilled 4f10 shell lying beneath filled 6s2 shell. This structure leads to very large angular momentum, L equals 6 and total equals 8. And it has very large magnetic moment. So magnetic properties of dysprosium have origin in this large orbital angular momentum, where large number of f electrons aligned on the outer relativistic outer f shell. So here I just show example of how 4f wave function look like, and that's a shape of wave function depends very much on the projectional angular momentum quantum number. Doesn't move. Why does it move? Yeah, frozen. Sorry. It's a new system. It just doesn't move slide.
No?
Oh, now moved.
Okay.
But what you have to click here? Oh my God.
I don't know, I think that.
That's it. Oh, doesn't work, huh? Yeah. Okay, sorry. So we calculate dynamic polarizability for a ground state dysprosium atom. And why would be interesting? A recent progress in trapping quantum degenerate gas of dysprosium by Benjamin Lett's group opened up the possibility of creating spin-dependent lattices for dysprosium. So we used exactly what I was told previously, experimental data about transition frequencies and transition dipole moment, altogether 62 experimental levels to calculate this polarizability. Dysprosium was used extensively in lighting industry that initiated a lot of spectroscopy in the past. So that would be convenient for us to use this information. We use a little bit of theory to contribute additional transitions. So, and we found very good agreement with calculation of average polarizability by Zuber and colleagues. But we also calculated MJ-dependent polarizability. And we found that in the infrared region, anisotropy and polarizability reaches about 1 atomic units. And it becomes much larger if we move to optical domain. Really strange. What's going on? Why? Does it have to stay like this? Okay, now we looked at the lattices with metastable ytterbium atom. Ground state ytterbium atom doesn't possess any electron spin, and therefore spin-dependent lattices cannot be created. However, metastable ytterbium has non-zero angular momentum and could have anisotropy and polarizability. Here I show a plot of, again, dynamic polarizability as a function of frequency, laser frequency for 3 different states. Actually, 6, but see, plus minus projection has the same value for this polarizability. So when positive polarizability indicates here that low field seeking states are trapped. Negative, it means they are not trapped. So for a particular frequency, which is YAG frequency, infrared region, so we can, what actually used in present day experiments to trap metastable ytterbium atom, only projection plus minus 1 are trapped, and 0, but not plus minus 2. But if you move to higher frequencies, it could be inverted. I would like to say a little bit about anisotropy in molecules, in molecular polarizability. Here, I show the case for potassium rubidium molecule, and it's only for 2 lowest rotational states, j = 0 and 1. And then actually we looked at the j = 1 with different projection of m, and then we can see that the difference, I mean, there is a large difference between polarizabilities for these projections. That could be even larger than 500 atomic units. I'm not going to talk about very much about to find some state insensitive trapping conditions. I just mentioned that polarizability could change dramatically if you influence molecule with external electric field. So it's easily we can find state insensitive trapping conditions for pair internal states. In this case, for j equals 1 and 0, we find that visibility will be the same as electric field strength equals to 10 kilowatt per centimeter. And that means that important for some experiments with microwave fields when trapping conditions across of a large sample of optical lattice will not change for this transition frequency. Now I move to anisotropy in interactions. So in general, interactions between atoms and molecules are orientationally dependent. And it becomes very important for low temperatures. When this orientational dependence become important and influential on the collisional dynamics. Here I just show a cartoon of free colliding atoms, which have 4 F-shell electrons, open F-shell electrons. And if they, for example, approach each other, then interaction energy will depend very much on the way how they approach each other. So when we talk about two interacting atoms or molecules, then spin and orbital angular momentum are added together. In case of a heavy atom, for example, then we look at the total angular momentum, not orbital angular momentum. And the body fixed projection of this total angular momentum is good quantum number. And the interest to these systems is due to very interesting long-range interactions between them. In case of magnetic atoms, there are 3 dominant interactions, which are magnetic dipole-dipole dispersion and electric quadrupole-quadrupole interactions. So this is well-known expressions. I just want to tell you that in case of dispersion, there are contributions isotropic and anisotropic. In case of anisotropic interactions, there are most strongest ones are related to coupling of quadrupole moment with rotation of a molecule. And then electric quadrupole interaction, it's rank 4 operator. So for each of these interactions, we find it convenient to define adiabatic C3, C6, and C5 coefficients by diagonalizing corresponding operator for each omega. So as I told, we used experimental data not only for polarizabilities of dysprosium, but also to calculate C6 coefficients. Here's example for C3 and C6 coefficients for this system. So I show only Gerada terms because when we look at the colliding two bosonic spin polarized atoms, then we need to look at Gerada systems in the ground state, of course. So there are actually 81 Gerada potentials dissociating to the same ground state levels. And in case of C free coefficient, so each actually circle corresponds to the potential, but we just separate it. We show separately behavior with omega. So the highest omega value, 16, has only one potential. But if we go smaller values, then there are many more potentials for the same omega. So same story with C6 coefficient. And I just covered this area with some color, which shows that sort of size of anisotropy for this system. And then in case of C6 coefficient, that we found that the value all positive, this corresponds to attractive potentials. So I just want to compare those interactions as a function of interatomic distance, again, for dysprosium atom. But I also included Zeeman splitting on this graph, together with anisotropic dispersion interaction, magnetic dipole-dipole interaction, red curve. And then I added two lines which correspond to general splitting between neighboring Zeeman sublevels at field 10 Gauss, 100 Gauss, and then rotational splitting as well for that molecule. So we know that Zeeman rotational and isotropic dispersion interaction just shift levels, but it does not induce spin flip or anything like this. But anisotropic interactions actually couple different levels. So I did not put here quadruple interaction on this graph because we done quite extensive calculation, ab initio calculation of quadruple moment for dysprosium, ground state dysprosium atom, and found it's very small. So this interaction potential is few order of magnitude smaller than any other potential, so it doesn't play serious role. Actually, we used it in our calculation. I will talk a little bit later, but it doesn't influence anything. So we try to see how we control interactions with Feshbach resonances. So we know in general Feshbach resonances appear when we also include magnetic field, and magnetic field increases, and then bound states could move up and then cross threshold, then resonance could appear. So without many details, I just explain that how we did calculate this Feshbach resonance spectrum, and we calculate scattering length and spectrum. So we worked with symmetrized channels with projection along now magnetic field direction. So here I show results of our calculation. It's adiabatic potential curves, long range, of course, potentials as a function of interatomic distance. So here, Zeeman splittings. And then we, in order to convert this problem, we need to include many partial ways because of the anisotropy in the system is quite strong. So we can see that starting like 170 atomic units, curves become coupled to each other, avoiding each other. So this certainly region, if atoms close to each other, for example, in optical trap, then they certainly influenced. They come in this region, and then anisotropy play a significant role. So here's an example of Feshbach spectrum that we obtained. There are few resonances, like half a dozen in the region of 300 Gauss. They have pretty nice widths, certainly observable, but we still hope that we could adjust our calculation to experiment, which is coming. And the only thing I could say right now that the position of these resonances can change dramatically if we vary depth of the short-range potentials, which as you have seen, there are 81 potentials, and its only experiment could help us to, really produce something significantly realistic. So I just say a few words that actually the nature of these Feshbach resonances in magnetic atoms are absolutely different from we have seen in alkali metal molecules, because it totally relies on anisotropy in interactions. And it's sort of interesting that it's constructive effect of anisotropy. It's not only bad things to have anisotropy. I would like to say a little bit about interaction between metastable atoms. You see, I told already that quadrupole interaction doesn't really participate in all this interplay of long-range interactions. When we looked at the collisions of ground state dysprosium atoms, but it is different when we look at the metastable dysprosium. For example, we just choose some metastable levels in stretch states. It's like 6s, 6p state, which is connected, not really connected, but it's accessible by optical transition from the ground state. And we found that quadrupole moment for this state is 17 atomic units. Yes, a order of 20 atomic units. So, but there are many metastable states which live long, so that probably some of them have even larger quadrupole moment. And here I just show potential curves for dipole-dipole interaction and for the quadrupole interaction in yellow, kind of yellowish-greenish color. For long range, looking at the maybe lattice 267 nanometer, when you actually have distance between lattice sites about 2,500 atomic units. So here I show those combined together, diagonalized those two interactions, and you can say that at distance 2,500, this dipole-dipole interaction dominates, and it has about 2 kilohertz value. So it's actually maybe useful. So about polar molecules of optical lattices, this is pretty known. I just maybe say very quickly that at present time, if we want to investigate dipole-dipole interactions between polar molecules like potassium rubidium molecules in optical lattice, then the interaction strength should be stronger than temperature. And at present time, when we analyze all information, then it's still much smaller. So that is size of the anisotropy in interaction for potassium rubidium molecules, and it's much, much larger than in dysprosium. So this is, I think I just go to conclusion. So that's, we have analyzed atomic molecular polarizability and characterized how well spin-dependent lattices can be created. And also we analyzed different long-range interactions, which is useful. And it shows that these systems are good candidates for studying exotic phases.
Have you ever tried to make calculation about metastable helium? Because you know that metastable helium
Yes.
is an extremely interesting atom. It is the only metastable of that kind which can get Bose-Einstein condensation, because there is a strong suppression of the staining ionization. And so there are a few groups in the world working in it, including mine. And why I think that the more information we can have about these atoms, the more useful.
Oh, you mean in anisotropy kind of things, what I was talking about? Or
Anisotropic by definition, because
yeah.
the reason why the staining ionization is suppressed is because we polarize the sample, and then with polarized atom, staining ionization are strongly suppressed, okay, by
Yes.
5 order of magnitude. But it's a good luck. But then there are plenty of interesting properties, including knowing more about Feshbach resonance and things like that would be extremely valuable information.
Oh, yeah. It's much more easy to calculate helium. I'm sure.
Somebody has to do it.
Yes, I don't know why.
Somebody has to do it.
Maybe from now on,
I don't think we have
all these theories start to do it, because it's much, much more easy. Yeah. No, in some sense, of course.
Exactly what is the real staining ionization
Oh, no, painting is much, it's difficult. I tried once.
Okay,
No, I mean, other properties may be
when we
helpful.
embarked in that, there was a calculation by Schlavnikov and company about this suppression. It was an order of magnitude, but we did the experiment and we measured it, because if he had not worked, then we would not have obtained Bose-Einstein condensation. So I think
Yeah.
there is room,
Nice.
and there is a group in Australia doing precise measurements, and Binbas and in Amsterdam also is doing precise measurements. We do precise measurements only when we need them. I mean, our goal is to use
I can
these
understand.
atoms.
Right, right.
Our goal is not to do spectroscopy or this kind of thing.
Right, right. That's,
But we have numbers anyway, because we need them. So I draw your attention.
okay, good. Thank you. I may send you emails sometimes.
So,
Yeah.
I can tell you who are the groups in the world working on that, and so you can check.
Yeah, when we shorten atoms,
with them.
we can go.
Know what are the experimental data available.
Yeah.
So for this program, how good are the experimental spectroscopic data that you use as input? Or maybe asking the question differently, how much of the uncertainty comes from, say, your calculations, and how much comes from
experimental data is very precise. Spectroscopy, it's...
I disagree with that. We've seen many mistakes.
You found some mistakes. Identification, maybe.
Yeah,
No, in our case, I mean, we have many more problems than experimental data. First of all, to calculate polarizability, you, in principle, have to include all transitions in the wall. But, of course, we don't have all of them, and we cannot produce all of them, even we try to calculate. So, but my experience with even potassium rubidium molecule, when we agree with Junier's experiment in polarizability, shows that you can restrict yourself to certain transitions, like few potentials, which are most important and connected to the ground state with dipole transitions. The others are two electron transitions or forbidden transitions, so they are not really very important. Of course, you have to put uncertainty, but in general, in a main term, you are right. So that sense, we never sure. It's a kind of a low boundary condition. So, and then, of course, to produce short-range potentials for dimer, for dysprosium dimer, is extremely difficult part. So it's sort of artificial kind of creation. It has to be there. You have to describe short range more or less decently. So we sort of connected smoothly to C6 coefficients, which we believe known better from experiment. And we implemented certain function as function, like dispersion function as a function of interatomic distance. So we smoothly connected all these things, but certainly have to rely on experiment to adjust these values. What?
In other words, are you including hyperfine interactions in the dispersion?
He is not. Bosonic, they don't have hyperfine.
Because you're including integers.
Yeah, right.
So can you include
Yeah, we did include already recently. And we do calculation between lithium, which has hyperfine, and ytterbium metastable. But here I didn't do anything. Huh? No, just, yeah.
interesting, for instance, if you sort of, Ben will be able to do this, but you can artificially turn off the anisotropy, turn off the...
Oh, yeah, I did. I didn't show it here. We did...
where these hyperfine resonances pop up.
that sense, of course, we didn't, but we turn off magnetic dipole, left only dispersion, anisotropy, or opposite. And we found they both important. Yeah, they both make something different if you turn off. But, of course, it would be interesting. Hyperfine, yes.
The fermions do, but it's not exactly applicable on
Yeah.
but you can still turn on and off. That's what I meant.
Yeah, if we do calculation with hyperfine, then we can turn off, of course. It's always, in theory, is nice in that sense, but not very accurate, probably. Thank you.